Bismillahirrahmanirrahim. Assalamu alaikum. In our previous video, we were discussing about converting from transfer function to state space representation, and we will continue our discussion. First, we will see how to convert this into block state space to block diagram, and then from state space to transfer function. This will be our today's discussion. So let's start. Here we have the state space representation. We want to convert this into block diagram. So we will have input R and output Y. So Y output is equal to x1, and also the x1 derivative is equal to x2. So if we integrate x both sides, so we will get the x1. So integration of x2 will be equal to x1. So first of all, output is equal to x1 like this. Here we have y is equal to x1. Also we have integration x1 derivative is equal to x2. So x2 derivative will be through integration will be equal to x1. So we will use integrator to convert x2 from x1. Similarly, again, one integrator will be used to convert x3 to x2, and x3 derivative integration of this will give us x3. But how to get the x3 derivative? By using this equation. We have x1, x2 and x3 already, and input r of t. R will be multiplied with the gain 24, will pass to the summing junction, 3 negative terms and minus 9x3. We have already get the minus x3 and gain with of 9 and minus sign, and minus 26 here with x2, and x1 will be multiplied with 24 and will be subtracted from this input to get x3 derivative. So this is the procedure to convert this state space representation to the block diagram using showing the phase variable. So transfer function with a polynomial in numerator. In the previous example, there was only a constant term in the numerator, that was 24. Now if we have a polynomial term in the numerator, so order of the numerator is less than the denominator. The numerator and denominator can be separated into cascaded transfer functions. So one will be used here, numerator will be here and denominator will be separated. So first we will separate these two separately one by one using phase variables. So x1 is the internal output. R multiplied with this term will give us the x1. X1 multiplied with the numerator will give us the output. Internal variables are the x1, x2 and x3. x2 and x3 will be used here. So the first transfer function is converted to phase variable representation in state space with x1 as output. So the second transfer function may be expressed as the second transfer function. The numerator is multiplied with x1 to give the output c of s. Also we can write this y of s. So taking inverse Laplace, we get the y of t is equal to b2 second derivative of x1 plus first derivative of x1 multiplied with b1 b naught x1, or to take the x1 derivative equal to x2, so x1 derivative will be equal to x3, x1 derivative will be equal to x2, and x2 derivative will be equal to x3. So here will be written x3, x2, and here will be x1. The output y of t is linear combination of state variable. Now this has become this linear combination. So we will now solve our first part, or the denominator part, this one. Okay, so for the denominator we will write this term multiply with x1. So let us first write this term. So r output over input, x1 of s over r input will be equal to this term, this transfer function, this term. This will be multiplied with x1 to give r of s. So we can write this, r of s will be equal to a3 s cube plus a2 s square plus a1 s plus a naught into x1 of s. So this term will convert this into time domain form. So the derivative of this x1 is already written as x2. So here will be x2, here will be x3, and here will be derivative of x3. So because we have three state variable, a multiplied with x dot x dot is equal to ax plus bu. As the state variable vector x has three terms, x1, x2, and x3. x1 is already written as the x1 dot is equal to x2. So here we can see that here we have x2 term, and x2 derivative is equal to x3. So here we can see that x1 and x2 term are equal to 0, and x3 terms here. The only remaining term is now the x3 term, x3 derivative, and here we have x3 derivative, this term. We will move all these three terms to the left side, and these will become negative, and divided with the a3 will give us the x3 derivative. So you can see that minus these three terms will be minus, also divided with a3. So a naught over a3 minus a1 over a3 minus a2 over a3. And also for bu, first two term are 0, here no r term, and for here we have my plus a3. So here we have written b with plus a3. Now the last step is to convert this state equations to this block diagram. So let's solve this. X2 integration will give us x1 as x1 derivative is equal to x2. So integrating this term will give us, integrating x2 will give us x1. Similarly, x3 integration will give x3 dot. So x3 integration multiplying with this integrator will give us x2, and similarly x1. Multiplying x1 with b1 b naught, x1 is multiplied with b naught and b1s. For this we need the output equation b naught x1. So b naught x1, b1 x2 will have used gain b1, and similarly b2 gain will be multiplied with x3. All these will be sum, move to the summing junction and give us the output c of t over y of t. So this will be our output. First two terms are very simple, we have already calculated. Now only these are used to find the x3 derivative. From here these are minus term, and so 3 negative signs. X1 will have gain of a2 a naught over a3, a1 over a3, and then a2 over a3. So input r of t multiplied with 1 over a3, and so this is our conversion of transfer function to block diagram. Conversion of transfer function to first state space, and then from state space we have converted this to a block diagram. I hope you understand this concept. So now we will move to our next topic, that is converting from state space to transfer function. This is also a very simple topic but requires some little concentration. So the state and output equation are given as, this is our static equation and this is the output equation. We want to convert this into transfer function. Transfer function is equal to output over input. So taking the Laplace transform and assuming the zero initial condition, derivative will be replaced with s, and ax of s plus b u of s, y of s, cx of s plus d u of s. From equation 1 we want x of s, because x is the, we want the input u of s. So output over input will be, from here we will get the value of x of s. We will place this value here, and then output over input will give us the transfer function. So from here si minus a over will be common and divided with here. We want, will take in inverse minus 1. So as these are matrix and vectors, so we have to be careful with solving this. So we will now replace this x of s in equation number 2. Y of s will be equal to c, and this is the x term, u will be taken as common. So this is the transfer function matrix. This is output. This will be output or input will give us the transfer function. This is our transfer function. If u of s and y of s are scalar term, we can find the transfer function. So this term, if we solve this term, we can get the transfer function. From state space, we know the vectors and matrix A, B, and C, D. So we will now work out on the example. Here, this is A matrix, is B, C, and D matrix is equal to 0. So we have to enter the values in the formula. C Si minus A inverse into B plus D. First of all, we will solve Si minus A. I is the identity matrix. So this is Si minus A. So this is Si minus A. This will be multiplied with C and B. First we will take inverse. So adjoint of A, this term over determinant of this. So we have solved this inverse. This is B matrix C and D. We multiply with C and B term. You see, so only 10 into this term will be remaining, as all these terms due to this 0 will become 0. So only 10 into s square, and also the b term, d term is equal to 0. So this will be our required transfer function. So we have to use only this formula to find the transfer function. This is our today's topic of converting state space to transfer function, and then from transfer function to state space. Thank you.